Okay, so this is not really on RDMFT, but so it's a talk about how to use natural occupation numbers for wave function ansatz states, and also apologies for all those people who have already seen this talk in San Sebastian. My talk on Friday is different; it's not the same one. So this is like a big collaboration project with Christian, Carlos, and also my PhD supervisor Adam Sawicki from Warsaw, and David Gross and Alexander Lopez from Cologne. Okay, so it had different aspects. It had like a physics aspect and a mathematics aspect, but I'll focus more on physics today. So to start, let's just imagine a fermionic interacting system. Let it be spinless, and there is some single particle Hamiltonian, so some overall potential, so it's all embedded in some potential, and there is some kinetic terms represented by the red arrows, and it all enters the little h. And there is some interaction, let's say it's two-body, where kappa is the strength of this interaction. So if kappa is 0, then we know what to do. We just have to diagonalize the local Hamiltonian, the little h. And this way we get some orbital bases and some energies. And the ground state is exactly the Slater determinant. So we create n electrons in the n lowest energy levels. Now if kappa is greater than 0, we can still use this basis to build the full configuration space. Right, so then we can keep this fixed, but then those coefficients will depend on the correlation strength. So there's capital N electrons in d spin orbitals. Okay, so now let's go back to kappa equals 0. We got this Slater determinant, so we can visually imagine the situation where a number of first lowest lying levels is fully occupied. So the occupation numbers are 1, and there is a number of completely unoccupied levels where occupation numbers are 0, and there's the Fermi level, which is the highest occupied one particle energy, Fermi energy. Now, if kappa is very small, then we can use some perturbation theory arguments to say that it makes sense to assume that our state is really of the following form. So there is a number of fully occupied core orbitals and a number of unoccupied orbitals, but around the Fermi energy, we allow for fractional occupations, and these are called active orbitals. Okay, so we just select around the Fermi level, we just select some active orbitals, and effectively we have some little n electrons on some smaller space, and then the ansatz state is called the complete active space ansatz. So because it's active space, complete because we take all the possible configurations. Okay. But now we can consider a complete active space self-consistent field ansatz, where if this is a variational quantum state wave function, then we optimize not only over the coefficients, but also over the active orbitals. So now we also rotate, consider all those basis changes. Some more terminology. This is actually most relevant for this talk, and also most general in a sense. So we can also consider multi-configurational self-consistent field ansatz states, where only a subset of those configurations enters the ansatz psi n. So some of these coefficients can be 0, just assumed to be 0, and then we optimize over the non-zero coefficients and again over the active orbitals. So this would be the NCSCF in short. So this talk will be exactly about such ansatz states. So let's look at the optimization a bit closer. So what we exactly have to do, we take the superposition of all our chosen configurations from some capital I set, And then also we consider the rotations of the single particle of the active space orbitals, right? So then what it means to find the MCSCF energy, it means to minimize over all the coefficients and over all those unitaries that enter the rotations of the basis. And this is quite complicated for a number of reasons, because computing those, the Hamiltonian in this rotated basis and those different orbital bases is computationally complex. Also, the minimization is over C and U, over coefficients and over the unitary, and they are not independent configurations, so they are coupled to each other. And also, in principle, there is a large number of configurations from which we can choose, and it's not a priori clear which are the best ones. So in this talk, I would like to show you some geometrically motivated construction, a systematic construction of such ansatz states that involve few configurations relative to this d choose n number. Okay, but to this, I will briefly review the notion of the natural orbitals and natural occupation numbers. So we consider the one fermion reduced density matrix, which is defined just like here, the expectation value of a f kj dagger f ki in some basis. This is a d by d matrix, and now this matrix can be diagonalized to obtain natural occupation numbers, which we assume that they are ordered decreasingly. And to each nk, there's an associated natural orbital, which are numbered from 1 up to d. Okay, and now in this language we can talk about Pauli constraints. So we can more kind of a bit formally we can look at it as taking some n fermion state, computing its one RDM, and then computing the natural occupation numbers from this one RDM, and we are asking what is the image of this map, right? So what are all the natural occupation numbers obtained from all possible pure n fermion states? So it is surely contained in this d-dimensional hypercube, right? So this we know as a Pauli principle. So each of these natural occupation numbers is between 0 and 1. And the CAS-SCF ansatz that I have just introduced is the same. We can say that this is the same as saturating a number of those Pauli constraints, right? Because we had the number of core orbitals which were fully occupied, and there was a number of virtual orbitals which are completely unoccupied, and there was a number of active orbitals which had some fractional occupation numbers. And this left us with some effective Hilbert space of some smaller dimension. And then the general strategy would be to start with some small n and d, and then increase the size of the active space to get more and more accuracy. But this is not the entire story, because we know that there exist generalized Pauli constraints. So on top of the ordering and then overall normalization, there are also some extra constraints. So for instance, if we have just 2 electrons or two fermions, then we know that the spectra are pairwise occupied, right? That's an old result, but there is also another old result by Boland and Dennis, which will be like this we will use for visualizing some examples today. So this is an example of 3 electrons on 6 orbitals, and then we have those extra relations that are written here. So recall that these are decreasingly ordered. So the largest plus the smallest is equal to second largest plus the second smallest. That's equal to the 2 middle ones. So their sum is always fixed to 1, and there is one genuine inequality which cannot be explained by the standard Pauli constraints. I mean, none of these can be explained by the standard Pauli constraints. But if we take now more electrons, or if you take now more orbitals, so 7 and 8, there are respectively 6 and 31 inequalities. So the number of those inequalities grows pretty fast. So this was an open problem for a long time until the breakthrough by mathematician Kriachko, who has identified this this map as a momentum map, which that you have already seen today, and it gave him a reason why these are all inequalities, and they cut out some convex polytope, and there is even an algorithm for finding this polytope. However, this is the algorithm is very computationally heavy, so the furthest Kriachko could go was 5 electrons on 11 spin orbitals, so not too much probably. But we will nevertheless use those results. So let's look at the Boland set, Boland-Dennis polytope once again. It's nice because we can visualize it in 3D. We can just pick 3 independent occupation numbers. So let's pick N6, N5, and N4. All the other ones are determined by this equality. And now this is the polytope. So this is not the Pauli hypercube. This is just because these are just 1/2 occupations, but it is contained in a cube. So these are some degeneracy. The faces. Some of the faces are given by saturating the ordering constraints. There is one Hartree-Fock vertex, some other vertices, and this phase comes from saturating this genuine inequality. Okay, so now from this we want to build some selection, some wave wave functions. So let's imagine, like now the simplest case. Let's imagine that our state has these occupation numbers, right? So it's mapped to the Hartree-Fock point. Then we can immediately conclude that our state is the Hartree-Fock state. So this is simple. But now what happens where our state, the natural occupation numbers of our state lie in the middle of this phase? So what if right? So what happens then? Then we have shown that there is another selection rule. So the very fact that our spectra lie here implies already a lot of structure for our state. So this implies there's quite a strong implication that our state is a superposition of those 3 Slater determinants. That's a mathematical fact, and it's not completely obvious. And the point is that it can be explained quite nicely geometrically. So this is the Pauli hypercube. So what we have to do, we take this phase and we extend it somehow to infinity, and we intersect it with the Pauli hypercube. And the vertices of the Pauli hypercube that are contained in this hyperplane, or plane in 3D in this case, are the ones that enter the ansatz. So that's the mathematical statement. So what happens in general? We have some D choose n vertices, the black, all the dots, black, and this one Hartree-Fock red dot. And we have some phase of the polytope given by Kriachko. And we say that our state is mapped to this phase. So now what is the ansatz? Take the hyperplane containing this phase and find those and select the configurations that are mapped to this phase. Okay, so that's just that's what this theorem says. So if occupation numbers saturate a generalized Pauli constraint, then the configurations entering the n-fermion state lie on the hyperplane containing that phase. So you might ask, what about an edge? So we are on the phase, but now let's say that the spectra are on an edge. There is a similar fact that we just have to extend this edge and see which vertices of the Pauli polytope are lie on this edge. So in this case, it will be 1, 2, 3, and 1, 4, 5. So this will be our ansatz. But now note that this is the CAS SCF ansatz, where with 1 electron sitting on orbital 1, right? Because it's 1, but no electrons on orbital 6. So somehow the CAS SCF is contained in our procedure. So just to recap the Boland-Dennis setting, we have constructed a kind of a nested family of MCS-CF ansatz states. The top state is just the Hartree-Fock vertex. Then we had this edge, which was just the CAS-SCF ansatz. And then when our spectrum lied in the middle of a phase, then we had this ansatz, which is not CAS-SCF, it's something more general. So what happens in general is that we would have some higher dimensional polytope. We would fix the Hartree-Fock vertex, and then we would draw such a diagram when this is the vertex. These are all the edges that contain the Hartree-Fock vertex. These are all two-dimensional facets that contain these edges. So for instance, this F22, it contains edge E3, and that's it. F42 contains edge E1 and edge E3. Okay, and then there are some, let's say there will be some three-dimensional faces of the polytope and such, again, some inclusion relation. And what our search, so to find some low energy within this scheme, you would just start with the Hartree-Fock and then look at, compute all the energies corresponding to those edges, pick the lowest one, let's say this one, and then we will look at all the two-dimensional faces that contain this edge, and then again write down the variational ansatz states corresponding to them, minimize, pick the lowest one, let's say it would be this one, and then move on to the higher dimensional, and then we would end up with some with some relatively low energy ansatz state. What is nice about those ansatz states? Okay. So the point is that we haven't done the numerics yet, but it's like an ongoing collaboration with Peter Knowles. But what is nice about those ansatz states constructed in this way is that they contain very few configurations. So let's look at some example. So this is an example of 3 electrons on 4 or on 8 spin orbitals. And this is, if you look at the Kliaczko paper by Kliaczko, you'll find, for instance, this inequality. This is a generalized Pauli constraint. So, and no spectrum of a pure state will violate it. But now we want to find the ansatz state that corresponds to this phase. So the procedure that I just showed you said that we have to find the hyperplane that contains this phase. So it means we change this inequality into equality, and now we want to find all the configurations that lie on this hyperplane. So we want to find all the configurations that satisfy this equality. So for instance, let's take this configuration 2, 4, 6. So it has such occupation numbers. So N2 equal N4 equal N6 equal 1, and the rest is 0. Now we need to plug those into the equality here. So we get 11 times 1, minus 13 times 1, minus 5 times 1. The rest is 0. So it's 11 minus 13 minus 5, that's minus 7. And that's different than 9, so this is not the right configuration. It doesn't enter the ansatz. Now, let's try another one. Let's try 1, 5, 6. So now 19 times 1, 5 times 1, and now 6, plus 5 minus 5 times 1 again. So it's 19 minus 10, so it's 9. So this is a configuration that lies on this hyperplane. So it does enter the ansatz. And now we have to do this for every configuration to find the ansatz. So, and these are all the configurations that will satisfy this inequality. In other words, if we know that our state, the natural occupation numbers of our state saturate this inequality, then our state is just is spanned by these configurations. That's like a mathematical statement. And also, Christian has another paper which says that if you are close to this to saturating, then this will be the biggest coefficients. So this will be like the biggest contribution to the wave function. Okay, so we got just 9 configurations out of H is 3, which is 56. So that's quite a nice truncation of the space. Okay, this is just a few words about methods, but that's maybe not so important now. So roughly the methods are about studying the geometry of this map, and this map, when you are at the boundary of the polytope, it becomes singular. So it has some non-zero kernel, and this implies the structure of the state. That's quite an interesting geometric fact. From symplectic geometry. Okay, just so to summarize, I have just introduced a construction of some families of MCS-CF ansatz states that are implied by quasi-pinning of the natural occupation numbers. Pinning means that they are close to the face of the polytope. Okay, and then there's this advantage that this is, first of all, a systematic way of using fewer configurations, and it also naturally contains the Cassel-CF hierarchy. So in this sense, it somehow it boils down to something which is like well used and well known. One disadvantage, obvious disadvantage, is that those polytopes are only known up to some 11 orbitals, so we cannot go too far with the number of with the dimension of the active space. However, those methods could be still embedded in some Cassel-CF method, right? So we could just say we have a number of core orbitals, a number of virtual orbitals, and some 11 active orbitals, and then we can use this for a larger setting. And also, a way to overcome this would be to find include spin conservation, and then this allows you to go further with the number of spin orbitals. And of course, numerical applications, which we don't have yet. Okay, thanks very much.